Good morning and welcome to this new session on policy control with functional approximations. In the last session, we have seen how the value prediction can be done with the help of function approximators. In this session, we will discuss the policy control methods with function approximations. So, by this session, we will come to an end to the part 1 of reinforcement learning. These reinforcement learning approaches are based on the state value pairs or state action value pairs. So, the objective of the agent is to maximize his return by choosing the best state and best actions. That is the key idea. But sometimes the state action values has no role in agent's learning. Such learning algorithms can be classified into non-associative learning that we will discuss in the coming sessions. So, this session will focus on how we can use function approximation to make policy controls. Okay. The main topics under discussion are approximation of state action values. That means how we will approximate Q values or state action values with the help of the weight vector from a function approximation. That is a basic idea how we can extend the concept of state value approximation into state action value approximation. The second point is on policy control approximation. There are on policy and off policy control methods. In off-policy control methods, we need additional information. Sometimes we need more domain knowledge. In the case of function approximation, the level of domain knowledge is very high compared to ordinary off-policy control algorithms. So that is a higher part of reinforcement learning that demands more research and more domain knowledge. So this session is confined into on policy control approximations only. And finally, we will conclude this session with a simple example of semi-gradient salsa pseudocode. How we can attain this policy control with the help of our function approximation. That will be shown in the form of a pseudocode in our familiar salsa in semi-gradient approach. Okay. First of all, let us see how we can approximate state value function. The key idea is just extend the updation rule for state values. So we will use the update rule SA to U instead of S to U in our state value updation. So in a sense, instead of updating a state value, we update state action value. Second point is how we will do this, or mathematically how can represent this function approximation of Q value. Try to approximate the action value at each state S as Q cap of SAW is equivalent to Q star of SA. That means this is my target. Q star of SA is my target. I am going to approximate this Q star of SA by a function approximation Q tilde of S comma A comma W. So my aim is to minimize this approximation error. As in the previous lesson, we will use stochastic gradient descent method to minimize the mean square error or average square error. What is W here? W is our key part. The W is the weight vector or weight matrix that is taken from the function approximation. In the case of linear regression models, the W, the weight vector, is a vector, d-dimensional vector. Sometimes it may be considered as an n-dimensional or n by n dimensional vector. That depends on the function approximator. Then how we will approximate the value? Approximation technique is very simple. We are not going to update the Q values by using our regular approach. Instead of that, I am using the stochastic gradient method, more specific stochastic gradient descent method, to minimize the mean square error in approximation. Now let us see what is the stochastic gradient descent function approximation rule for Q values. The general gradient descent update for action value problem is just an extension of the same thing that we have derived for the state value approximation. The formula is like this. Wt plus 1 is defined as Wt plus alpha into Ut minus Q hat of St At Wt into gradient of this Q hat of St At Wt. So instead of the state values V cap, I am using Q cap with specific action. That is the only difference. So it is just an extension of value updation rule in state value. Then this Ut is an unbiased estimator for the Q pi of St At Wt, because this Q pi, the state action value under the given policy is not known. In that case we use an unbiased estimator, and that unbiased estimator is Ut. Now we move on to function approximation for one-step SALSA. How this function approximation can be done for SALSA? This is our usual rule. Omega t plus 1 or Wt plus 1 is equal to Wt plus alpha into Ut minus Q hat of St At Wt into gradient of Q hat of St At Wt. Remember, this hat symbol indicates that it is just an approximation with the help of this weight distribution. Then how we can update this rule, this general updation rule for one-step SALSA? Idea is very simple and straightforward. We replace this unbiased estimator Ut by one-step SALSA return. What is one-step SALSA return? That is simply Rt plus gamma into the corresponding next stage return, next action return at the state St plus 1 or S dash, whatever it is. So in simple language, this Ut can be replaced by Rt plus 1 plus gamma into next state action value for At plus 1, that is Q hat of St plus 1, At plus 1, Wt, minus the minus factor is here Q hat of St At Wt itself, then gradient of this Q hat of St At Wt. So remember, this approximation itself contains Wt, so the difference contains more noise in error measures. In that case, this method, this gradient method is called stochastic semi-gradient updation rule. In real cases, that is instead of this Q hat of St plus 1, At plus 1, Wt, suppose we have Q pi of St plus 1, At plus 1, that means Wt has no role in this next state bootstrapping. In that case, this same formula is known as stochastic gradient descent. It is semi-stochastic gradient descent. Why it is called semi-stochastic gradient? Because this updation need not be moved in the minimum error direction. Normally, the stochastic gradient descent algorithm always grow in the minimum error direction, but unfortunately, this expected value or this Qt Ut that is taken from one-step SALSA, it involves Wt, so it is again an approximation, and so this difference contains more noise or more error, and hence this weight updation rule need not be moved in the same minimum error direction. That is why it is termed as semi-gradient or semi-stochastic gradient descent algorithm. That's all. It is not a new algorithm, the same algorithm, but there are some mismatches in the case of the rules or definitions of stochastic gradient. That is why we call it as semi-gradient or semi-stochastic gradient. The term stochastic is come because we make use of samples to calculate this weight updation. So sample updates need not be the original update values, so it is stochastic in nature. It will change with the set of samples that we are using. Okay, so then For a constant policy, if we are using a constant policy for this one-step updation, this method converges in the same way that TD0 does. Because in TD approximation, instead of Q tilde, we use V. If we are using a constant or stable policy, this Q value will be approximately same as the state value, because from the initial chapters we know the state value is same as the maximum of Q values. In stable cases, this selected Q values, especially greedy policy, the Q values will be same as V value. And that case, this weight updation is same as TD0. Also, mathematically we can say that this weight updation or this method, that is function approximation on Q values, converges in the same way as TD0 does. That's all. Now we think about policy control method. In the last few slides, we have seen how to define Q values for corresponding states with the help of function approximation, and now we also discuss what is a stochastic gradient descent method or semi gradient descent method to minimize the error. Okay, now we come to how to control learning or policy control for these agents movements. I once again remind you, the policy control means we control the agent's movement in the reinforcement environment. How we can control him? By revising the policy. All the movement of this agent in our reinforcement environment is according to a policy. By changing the policy, the agent movement will control. So the policy control means, or the control on agent means, we just update the policies. Our trivial concepts in TD learning and Monte Carlo, we try to update learning rules using some greedy policy or epsilon greedy policy. We are using the same thing, but the value updation is not happen directly. The value updation is automatically happen or intrinsically happen by weight updation. That is the only difference in this extension. Okay. Now let us move on to various steps in policy control method. The steps in policy control is given by, first of all, set an initial policy approximation, then make policy improvement. Only two steps. First step is we set an initial policy approximation, because we don't have any strict policy in this function approximation cases. We set up an initial policy for this agent and then we improve that policy. That is the key idea. So how to set initial policy approximation? The easiest way is you just scan through all the states in the environment and select the greedy action. You just select the greedy action for each state. So it defines a policy that defines the movement for the agent. So the agent will learn a greedy policy. Then we update the greedy policy with the help of some soft greedy approach or epsilon greedy approach. That's all. First step, choose an epsilon greedy policy, not epsilon greedy, full greedy policy for each state. Then it will define a most greedy policy for this agent. At that state, the problem is it will not explore various states. So in order to maintain a balance between exploration and exploitation, we will choose epsilon soft or epsilon greedy policies for policy improvement. For initialization we use greedy approach, but for improvement we will use epsilon greedy or epsilon soft greedy approaches. Okay. For each action A in state S, compute Q hat of STATWT as we have discussed in the previous session, and then find the greedy action. A T star is equal to argmax A Q hat of STATWT. That means I select that action A which gives the maximum Q value. Then it is termed as A star of T. This is for state ST. We will do the same for every state. Now connecting all these actions we get greedy policy. That is our initial policy. Now we improve this with the help of some epsilon greedy approach. So next step is policy improvement. Change the estimation policy. Now the greedy policy will change with the help of an epsilon greedy or soft policies to a soft approximation of the greedy policy. That means in the policy improvement we are not going to change the state values or state action values. We just change the weight updates. Then how we will do this? We do this with the help of choosing the action with epsilon soft policies, not greedy policy. Then actions are selected according to the same policy. So in essence, the policy control method has two steps. First step is initial policy by greedy approach and policy improvement by epsilon greedy approach. That's all. Now, to get a good understanding on this working, just look into an example, that is semi-gradient salsa. Input is a different action value function parameterization q hat from s cross a to x cross a cross rd to r. So this is action. State value case, that s is from s cross rd to r. This q hat contains both state and action information and also the weight updation in the case of function approximation. In original cases, q of a s, in that case only s cross a, but here q hat means this q hat of s comma a comma w. It's a triplet, and definitely the domain will be s cross a cross the domain of w, that is d-dimensional real space to real number. Then algorithm parameters, that is our learning rate alpha, it should be greater than 0, and we choose an epsilon greater than 0, that is for epsilon greedy approach. Initialize value function weights w arbitrarily. You can choose w is equal to 0 or any random number. Loop for each episode. Remember, you have to repeat these iterations over various episodes. So I start a single episode, then I fix a state and action, then initial state and action of the episode. We choose it by epsilon greedy. Loop for each step of episode. I choose an episode, that means I start from the initial state S0 and leads to the end state or ST. The complete path is called one episode. Okay. Take action A, observe its reward and next state S dash. If S dash is terminal, that means we are at the terminal state, then the next state return will be 0. We won't get anything from the next move. So the updation rule becomes w is equal to w plus alpha into the immediate return r minus q hat of s comma a comma w. See, this is the two updation rule. First updation rule is for our terminal state. This is for the non-terminal state. Compare the difference. The difference is that in non-terminal state there is one more term, gamma into q hat of s dash a dash w. That term is not here if the state is in terminal state. Why? Because this term is applicable only for the next q value, that is next state q value. In the terminal state there is no next state. That is why this term is absent. Okay. Then go to the next episode. If it is an end terminal, then we will go to next episode to update the state action values. Choose a dash. If it is not a terminal state, I choose the next action a dash as a function of q hat of s dash comma w. We are not specifying here any action because that action is our choice. This choice should be epsilon greedy. Okay, we choose an epsilon greedy policy there. Then the weight update. W is updated by current w plus alpha into immediate return or reward at that state plus gamma into q hat of s dash a dash w minus q hat of s comma a comma w into del of q hat of s comma a comma w. This is our usual SASA one-step updation. If that updation will happen, just move on to the next state. Then action is also updated. Then there is a question where we update the q values. The q values are updated automatically. Q values will be updated automatically with the help of this weight updation, because each q value is calculated in terms of state, action and weight. And how the actions are selected? Actions are selected using our epsilon greedy policy. So to automate that procedure, we are not explicitly update the action values here. We update only weight values. These weight values will be used to calculate q values. That is our original q value calculation policy. Okay, this is a trick behind this episodic semi-gradient salsa for estimating an approximate policy q tilde from a weight update W from a function approximation. Okay. So this is all about Q value updates with the help of function approximation. We just imitate all the procedures in state value updation by we incorporate actions. In the case of selecting actions, there are two conditions. One is how we select the action, then how we update the action values. Both these ideas were explained in this session. In the next session, we will start the non-associative learning, especially the reinforcement algorithm, that is called the reinforced algorithm. It's a popular algorithm for non-associative learning. This non-associative learning is a common term in behavioral psychology that is deals with animal learning. That means the response or there is no relationship between our stimulus and learning. The stimulus need not to create any learning. For example, if we consume a particular type of food every day, automatically our interest in that food will decline. That means I like a particular food item, for example vegetable biryani. If I ate vegetable biryani every day, then what happened? I lost the interest in that particular food item. Okay, this is an issue. That means the stimulus is there, but that stimulus need not create any learning, because that stimulus is my interest in that food, but a continuous consumption leads to loss of interest. That means in our machine learning approach, it is a new interpretation. That means non-associative learning means we are trying to generate a new idea that will not depending on the state and action value. In the current up to the current session, we will discuss the state action value context. How the agent learned from the state action values. How it happened? Agent's aim is to maximize his return, that is depending on the state action value pairs. But in non-associative learning, the state action value has not that much significant, but we add some parameters for that. The parameter will decide the learning of the agent, or the context will make some learning. Okay, it is not the stimulus but the context. In psychology, it is termed as some habitistic learning or habitistic learning environment, etc. But we are not going to discuss that psychological aspect. We start from the basic psychology, then come into our reinforcement learning approach. Okay, that's about the basics of non-associative learning that we will discuss in the next session. Thank you.